All right. Hi, everyone. Welcome back to the Data-Driven Methods in Science and Engineering seminar. We are very excited to have Professor Richard Baraniuk with us today. Richard is the Professor of Electrical and Computer Engineering at Rice University. He is also the founder and director of OpenStax, a nonprofit educational and scholarly publishing project he founded in 1999 to bring education into the internet age. Frankly, while preparing this bio, I found it quite challenging to do justice to all of Richard's accomplishments in one 1-minute introduction, but here are some.
No need.
But no, only some. So Richard is a member of the National Academy of Engineering and American Academy of Arts and Sciences. He is also a fellow of the National Academy of Inventors, American Association for the Advancement of Science, and the IEEE. He has many inventions and co-inventions, holding 40 granted US and 6 foreign patents, 6 of which have been licensed to Siemens to radically accelerate MRI scans. He has also received many awards for his research and inventions, which are too numerous to count here. Richard's research interests in signal processing and machine learning lie primarily in new theory and algorithms involving low-dimensional models. His research topics include the theory of deep learning, compressive sensing, multiscale natural image modeling using wavelet domain, hidden Markov models, and time frequency analysis. So today, Richard's gonna tell us about his latest work on the geometry of deep learning through the lens of approximation theory. Richard, thanks for being with us, and take it away.
Thanks so much. It's great to be here. Thanks for the invite. I'll jump in. Let me share my screen. How's that? Good?
Perfect.
Okay, well, great to be here. I'm going to talk a little bit about some of the work we've been doing at Rice for the last number of years on looking to understand what goes on inside deep learning systems. And the particular approach that we're going to look at is using the idea of approximation theory, which you might view as the pinnacle of mathematical development in order to understand what's going on inside deep nets, why they work when they work, and we'd also like to know why they don't work when they don't work, so that we can make them better. Feel free to interrupt me with questions. I'm not going to probably see the chat just because of the way my screen's set up, but just feel free to blurt out questions. We can keep this really relaxed. So we're going to talk about deep learning today, and we're really all deep learning is a way of solving function approximation problems. And here's 2 examples of function approximation problems that come up all the time in machine learning. One is object classification. For example, we're going to input a digital image, a picture, as our input X into this system that's a function of X, parameterized by parameter theta. And what we'd like to get as an output, Y, is a inference about some description of this image. Is it a boat? Is it a cat? Or is it a picture of Paul, for example? And this is called classification. Another problem is regression problem. Here you might want to go function to function. This is just one example of taking, for example, some seismic imagery and some well logs. Those are those vertical stripes on the left. And what you'd like to do is infer the impedance of the Earth from this. So this would be an example of a regression problem. And this is these kind of problems have been around for forever, and there have been a host of different methods to solve them. But today we're going to be looking in particular at using deep networks for solving these kind of problems. And the neat thing about a deep network is that they're hierarchical, right? What they do is, rather than just computing, given an input X, computing the output Y in just one shot, they actually compute via a composition of simpler operations. So we have an input here. Hopefully you can see my cursor, input X. It goes into a first operator, and the output of that goes into a next operator, this blue operator, and that output goes to another green operator, and so on. So we're forming our overarching approximation hierarchically by this composition. And of course, this is deep learning, so we can't use the term operator. We have to invent new jargon. So these are called layers in deep learning. Okay, and now we can actually pose what is really the grand, as far as my group thinks, the grand challenge of deep learning, and that is that deep nets are just incredibly easy to describe locally. So what do we use to build up these operators or these layers? It's just really simple operations like multiplication by a matrix plus a bias. So just an affine transformation, and maybe the matrix in the affine transform is a convolution matrix. Okay, so it's extremely simple. Another example: take a vector input and just throw away all the negative entries in that vector. Right, just a thresholding operation. Right. Another example is a subsampling. Right, taking an image that is say large with a lot of pixels and creating a low resolution version of it, right, by subsampling. Of course, this is deep learning, so we can't call these thresholding and subsampling. We have to give them new names, and folks refer to this. Scalar thresholding is the ReLU, rectified linear unit, and subsampling we actually refer to as pooling. Okay, but nevertheless, these are very simple local operations. But it's a grand challenge because nobody really knows what happens once you compose 100 of these in sequence. So it's not really clear how to describe what goes on globally, right, as you form this composition, right? And as a result, since it's not really clear what's going on, folks have treated deep networks by and large as black boxes, right, with a zillion parameters. And so you have a set of XY training data pairs, you have millions of these, you have billions of parameters. Actually, I just heard the other day, there are now deep networks with trillions of parameters. And then you use some kind of gradient descent in order to optimize these parameters, right? And this is crazy because it's worked spectacularly well from an empirical perspective. But it's just powerful and has led, all this empirical progress has led some among us to like muse that maybe deep nets are taking us to some higher intellectual level. But I would argue that they actually aren't. They're just inscrutable and mysterious. And so all our work is to try to take some of the mystery out of these methods. So what we're going to talk about today is that you can think of deep networks as performing spline approximation, and that this it turns out to be a really quite useful way of looking at deep nets. So that's what we're going to spend the next while on. We're not the only people thinking from this perspective. There's a cottage industry of us now thinking about these ideas. But one of the I think key differentiators of our work is that we're thinking very deeply about as we're going to see, the geometry of these spline approximations. So let's jump right in. Let's just review what a spline approximation is, and we're going to the good news is that we are going to deal with the absolute, pretty much simplest kind of splines. So no B splines here, or cubic splines or anything like that. We're just going to do simple, continuous piecewise affine or continuous piecewise linear spline approximation. Okay, and so splines, there's a yin-yang kind of relationship between two parts of the spline approximation. So let's say we want to approximate this dark blue curve here. Well, the one part is we take the input variable, which is x in this case, and we partition the space of that input variable, partition the domain into regions, which in this 1D example are just intervals. So we have a red interval, a green interval, a blue interval. And then that's the one part, the yin part of our approximation. And then the yang part is over each of these regions, the red region, the green region, and the blue region. We approximate the function with just a straight line, right? And in higher D, it's a hyperplane. So this gives us a piecewise affine approximation. And then finally, it's CPA, where the green and the red lines meet, we have to have continuity, right? So we have to have these pieces match up. Okay, so this is a simple case in 1D. In high D, everything, the concept is the same. You partition the domain. The domain now is going to be some high dimensional space. And so instead of intervals, you'll have polytopes, right, in high dimensions. And then on each polytope, you'll have a hyperplane. Okay, hopefully this makes sense to everybody. So there are two different ways of, roughly speaking, fitting spline approximations. The first is the powerful way. And this is so-called free knot splines. What I mean by this is that the orange dots are allowed to be anywhere, right? Anywhere in the domain, right? These orange dots are actually called the knots of the spline. This is the most powerful way of approximating a function. You get the best approximation error. Unfortunately, it's just computationally intractable, right? Even in 1D, it's expensive, and you go to high D, it's not even clear well, it's basically an NP hard type problem. Okay, so that's unfortunate for this powerful method. So what people have generally done is they've gone to like some fixed partition, right? That's like an easy approach. And if you think about a dyadic grid, and you think of splines on a dyadic grid, well, that in fact gives you wavelets. So if you know about wavelet transforms and subdivision methods, the nice thing about that is then we don't need to think anymore about where the knots are. We just need to think about optimizing the local mappings. Okay, but we're going to see that deep networks are somehow in between these two, and they give you a lot of the power of free knot splines, but they are computationally tractable, right? So let's dig into that. So the crux of everything I'm speaking about today, the really lucky thing, is that I'm going to use the word all for the rest of this talk. It's not really all, but it's virtually all of today's deep net architectures, all the ones you read about that perform great. They're all constructed from layers, right? These red, blue, and green operators that are all continuous piecewise affine operators. This is very lucky. Don't have to be, but just turns out that they are. Okay, and so what does that mean? That means that since the layers are CPA, it basically means that the layers are CPA splines, right? They're not spline functions, they're spline operators because they have a multi-dimensional output. So that's nice. That means that we have certain nice convexity properties with respect to a layer. And a multi-layer deep net, so since a spline of a spline of a spline is still a spline, a multi-layer deep net, even from the input to the output mapping, is just another continuous piecewise affine spline. Okay, so this is kind of very it's kind of semi-obvious to just to notice. So let's look a little bit more into how a deep net builds up a spline approximation. Let's think about just this single layer with that takes. Let's say it's the very first layer of our deep net, just to keep notation as easy as possible. So we take an input X in blue here to, and it's 2D, just so we can visualize, to an output 5-dimensional Z is the output of that layer, and it's got a 1 because it's layer 1. So what are we doing in this layer? Well, this graph is indicating, basically just saying, take X, multiply it by a matrix W with 2 columns, 5 rows, and then add on a bias vector with 5 entries, affine transformation, and then take that affine transformation and run each entry through this ReLU, right? Just throwing away the negative values. This is sort of the bread and butter operation that goes on in a deep net. And now we can start to let's just write this out in a bit more detail. Right, so let's just look at this single output, this particular output zk at this first layer, right? In this case, k is 3 over here, right? Well, the computation for zk, right? So zk out of the first layer is going to be the ReLU, the thresholding of the kth row of our W matrix, inner product with our input, right? So this is the kth row of our matrix, inner product with the input. Add the single bias entry from the kth entry in the first bias vector, and then basically threshold. Hopefully this makes sense to everybody. Very simple calculation. And now what we can do is we've understood a little bit about the computation of z from x. We know that this is a spline operator, that the mapping from x to each of the entries of z is a CPA spline function. But what is the part? So that's easy to see. But what's less easy to see is what's the partition of the input space, right? Because now our input space is two-dimensional. So remember, a spline has not only the approximation with hyperplanes, but it also has the partition over which those hyperplanes live. So what's the partition? Well, it's actually easy to figure out, because this computation in the inside of the ReLU, the thing where I have this red bar, this is simply the equation of a hyperplane in the input space, right? This is a hyperplane. What does WK do? WK simply steers the angle, right, of the hyperplane in 2D space, and B shifts the hyperplane, right? So what we just basically have now, by piping this, or by processing this hyperplane computation through this ReLU, or this thresholding, right, the output Z will either be positive, right? It'll either be either the inside here is positive, and so Z will be positive. That corresponds to being on the bottom, the bottom half, where am I going here? The bottom half of this hyperplane. Or the input will be negative, which means the output will be 0 and will be in the upper half of this hyperplane. Okay, so hopefully you can see this. And so if we have, in this case, if we have like 5 different outputs in our vector zk, that we will be throwing down 5 hyperplanes in this two-dimensional input space. Okay, and these 5 hyperplanes are forming a hyperplane arrangement, right? And this hyperplane arrangement, which let's just go, this hyperplane arrangement is going to define the partition, spline partition of the input space. Okay, so basically what that means is, well, actually, let's just go forward. That if our input falls into this particular point in the input space, then this is one particular partition region or tile of our spline function. So basically, given that x falls in this region, we can go look up in a table, right? And that will give us the entry Q of x that basically tells us which matrix A and bias vector B to grab out of some table of A's and B's, right? And then we're going to simply apply those as an affine transformation to x, right? Because what is a CPA spline? It's just a local affine transformation. So the local region is described or defined by this hyperplane arrangement, and then we just have a different A and B for each of these. Hopefully this makes sense to everybody. You move to a different region, you have a different A and you have a different B, okay? And you can compute these A's and B's, okay, analytically. So where do things get interesting, right? They get interesting not thinking in terms of the spline function approximation or operator, but really in terms of the geometry of this, this tiling. So let's dig into this a little bit deeper, and let's just remember what we talked about, about 5 minutes ago, and that is not only is one layer of a deep net a CPA spline, but any combination of layers, including the entire input to output mapping, is also a CPA spline operator. Okay, so now what we're going to do is we're going to talk about two layers. Okay, so the first neat thing that you can learn is that we know that if you go through the first layer of a deep net, then you're basically going to be partitioning the input space via this hyperplane arrangement formed by throwing down hyperplanes, where each hyperplane corresponds to one of the outputs, right? Output units or neurons of your network. Okay, so this is an example, and again, for this very simple 2D input space so that we can visualize. Now what happens if we go through 2 layers? Okay, well, going through the first layer, we see the picture here, we're going to have these in this case, there were six outputs, and so we had 6 cuts, okay, for this particular picture. So now what happens when we take that output of that first layer and now go through a second layer? Well, the first thing to remember is that we can ignore the first layer and just think about this second layer. It is again just a CPA spline. It again is going to form a hyperplane arrangement in its input space, right? But its input space is the output space of the first layer. Okay, so what happens is these hyperplane arrangements interact with each other, and they interact in a really interesting way. In that, if you have a 2-layer network, the hyperplanes from the first layer, once you put 2 layers together, these black cuts here are all remain in the tiling of the second 2 layers together. Okay, so these are noted gray here. You see they're all the same. But then there are going to be new hyperplane cuts caused by the second layer. And the really neat thing is that these cuts are when you think of them in terms of the input to the second layer space, they are flat, they're straight. But once you pull them back through the first layer, they're actually going to fold. Okay, and you can see one of these here, a folded hyperplane. This is a cut that was straight in the second layer, but once you go through 2 layers, it's going to fold. And if you think about it, the reason why they fold is that we need to maintain continuity of this mapping. And if they didn't fold, you wouldn't have a continuous piecewise affine mapping. Okay, and the neat thing is we can actually compute the dihedral angles of this folding. Right, it's just in terms of these A's and the B's that we've already just talked about. Okay, so where might this be interesting? Just thinking about applications of these ideas. Well, let's think about a multi-layer network that's doing binary classification. So is it a picture of a dog or is it a picture of a cat? Okay, well that just corresponds to a whole number of layers that you're going through in your deep net. The final layer will simply have a single output, right? And that single output will be either dog or cat, right? Or like 0 or 1, okay? Dog images on this side of this red line and cat images on the other side of this red line, okay? And the interesting thing is that this decision boundary that's formed by a deep net with cats on one side, dogs on the other, is just another hyperplane cut. It's a hyperplane, but that hyperplane is then pulled through all of the subsequent layers to get to the input, not subsequent, frequent, I guess, layers. And it folds multiple times, and this is what causes the decision boundary to snake around in the input space. Again, with dogs on this side and cats on this side. Since we can compute these dihedral angles, right? Whenever we go through one of these folds of the decision boundary, we can actually start to think about generalization properties of a deep network, which are highly dependent on the smoothness of this decision boundary. Well, think of dihedral angles. The closer the less bendy the hyperplanes, right? The smaller the dihedral angles, the smoother, if you will, the decision boundary is. So we have a lot of work going on in that direction, and be happy to talk about later. So hopefully this gives you one like application of these kind of ideas. Let's keep going. Let's keep talking about this subdivision process of deep networks. And I forgot to mention it earlier, but let's just kind of go back. It's a relaxed audience, right? This is a little bit, if you just kind of suspend belief for a minute, this is a little bit like wavelet-like, and that's why we use the term subdivision is correct here. That basically what you're doing is taking this coarse spline partition that's formed by one layer, and now you're forming a much finer partition with this two-layer network, because the hyperplane cuts from the second layer are subdividing, right, the hyperplane arrangement from the first layer. So hopefully that makes sense to everybody. So you can think of deep nets as a way of using subdivision to really efficiently create a highly complicated spline partition. Okay, hopefully that makes some sense. So what can we say about this partition? Well, it turns out you can say some interesting things from a computational geometry sense, and that is that these tilings that are created by deep networks, which turn out to produce convex polytopes. Okay, well, it turns out they're very closely related to Voronoi diagrams. Okay, which again relates closely to ideas like k-means. Well, it turns out they're not exactly a Voronoi diagram. They're a generalization called a power diagram. So probably everybody on this call knows about Voronoi tilings. Maybe nobody's heard of power diagrams, but basically it's the same idea. What's a Voronoi tiling? You have a set of centroids, and then you use, let's say, you associate with each centroid a tile, and a point is in a tile associated with a particular centroid if it's closest to that centroid in, let's say, Euclidean distance. Well, if you extend this idea of Euclidean distance to something called Legendre distance, which is it's like a biased, it's a Euclidean distance plus what's called a radius term, which is basically like a bias. Okay, then you get it's like a warped Voronoi tiling, and you can prove that any of these modern deep networks, the spline partition is always a power diagram, right? So it's like a Voronoi diagram, but you can warp certain tiles to be bigger than others. Okay, but power diagram tiles are always convex polytopes, which is means they're very attractive for analysis. And we actually have, again, you could get closed form formulas for the centroids and these radii, just in terms of either these A's and B's, the affine transformations, or the weights of the deep net. So you can study this tiling in really quite a bit of detail. So let me just wrap up what we've talked about up to now, and the basics basically, and then let's launch into 3 examples of this theory. So what I'm claiming in this talk is that deep nets are a tractable way to do spline approximation from samples of functions. You don't get access to the function, you just get access to samples of a function that live in very high dimensions. Okay, and if you took this, it's really important to note that this is an extremely difficult problem, right? Spline approximation, like free knot splines in like higher dimensions, it's not even clear how to even define what you mean by free knot spline. Okay, and so this is I think the thing that makes deep nets, I think, so interesting from a theoretical perspective. And the important thing, the tractability is key, and it results from the fact that we're hierarchical, right? The fact that we're using a composition of these simple layer operators that where we build up this partition in terms of using subdivision, right? Rather than defining the tiling like a priori. Okay, so we're taking training data and we're adapting the spline partition to that, and then also the spline CPA approximation. Hopefully this makes sense. Maybe I'll just pause and ask if anybody has any questions at this point before we launch into some examples.
So maybe, Rich, I can ask just real quick. So it seems like basically, just to summarize it, so you basically, the deep neural net basically sets up in some space a Voronoi tiling of where the patches are labels. So another way, maybe
patches are labels. Let's unpack that.
Yeah. Well, maybe every tile, right? Is that a dog?
No, good question. Yeah, no, I think I was unclear. Yeah, I was very unclear. So thanks for that. That's a really good question, because I think I was unclear. Let's just say, and I can use this picture right here. Let's just say we want to use a deep net to approximate, like an upside down bowl, right? And here, upside down bowl. And so, but we don't have the bowl. All we have are samples from the bowl, right? And so we can think of those samples, of course, have like an x coordinate from the input, right? The horizontal plane, and then they also have like a y height, right? In this case, the y height. Okay, and so that's all we're given are these xy pairs, right? And here you can see these dots are the x coordinates, right? Of those of our data points. And then you could imagine stretching vertically from each of these, right, would be to appear, right, some y value on this true bowl, upside down bowl. Make sense? Okay, so what we want to do is we want to learn an approximation of this bowl just from these xy samples. Okay, and so what happens is as we're learning, I'm going to talk in a minute about learning, but let everybody knows that you don't just take a deep net. You take a deep net and then you do some kind of optimization, right, in order to tune the weights, in order to learn this upside down bowl. So what we're going to do is once we've as we're learning, what we're basically doing is we're tuning some straight line cuts here in this two-dimensional input space, right? Because we're doing multi-layers, these straight line cuts from later layers have to bend, right? Have to like break. And so in the end, what we get is a tiling. But that tiling is just a tiling of the input space. As you can see here, we might have multiple points in each tile. We're going to have tiles with no points in them, right? But that's just the partition of the input space. Here they happen to be triangular because I just pulled the random picture off the internet. But in general, they're just going to be called, convex polytopes, right? And then what corresponding to each of these regions, we're just going to have, like say this region right here, we're going to have a corresponding affine, like a hyperplane, right, up in this higher dimensional space that those hyperplanes together form this CPA approximation to our upside down bowl. So does that help, Nathan?
Yeah.
That I was super unclear there.
No,
what I've kind of pointed to here is a kind of like a regression, what you'd call a regression problem, right? There's no dogs, no cats. We're just trying to fit like a surface.
This is right. Okay, perfect.
Yeah, but but now let's just say let's say that some of these red points corresponded to dogs and some corresponded to cats. Okay. Well, then what we might have in this. Well, actually, no. Let's not even go there. Let's just keep going. Can I keep going? Because it breaks down. My example breaks down in this case.
Okay. All right.
Okay. Can we keep going? Any other questions? Okay. I'm going to do two examples because up to now, it's really just been setting up this like framework, right, to be able to think about deep nets in terms of splines. So let's see what we can do with it, and let's look at 3 case studies of what we can do with it. And the first one is like I'm excited because like brand new, right? Brand new, and this is looking at the impact of the so-called architecture of a deep net on learning. Okay, and so let me just remind everybody what I kind of said really glibly a couple minutes ago, and that is like if you're a deep net practitioner, right? What do you do? Well, you have a problem. Let's say you have a problem that you want to solve, right? Some approximation problem, and you have training data for that problem. Let's talk about so-called supervised learning problems where you have input and output pairs, inputs X, outputs Y. And so you have your data, you have your task, you have training data, and then you have to choose an architecture, right? So there's not just one deep learning architecture. There are like zillions of them, right? We'll talk about some of them in a second. People have heard of things like convolutional neural nets. Well, that's just a particular kind of deep learning architecture. So you have to choose an architecture. So now you choose your architecture, and then what you do is this architecture has, again, zillions of parameters. You need to tune, you're going to tune those parameters in such that when you put in a piece of training data X, the output of the network is close to the y that from the training data. Okay, I'm doing a lot of hand waving here instead of showing you a picture, but hopefully that kind of makes some sense, right? And how do you do this? Gradient descent, right? And so let's like now jump into our application, right? Let me just kind of say it again with this particular picture that we have here. We'll have a particular X, a picture of boats, and then we'll basically put that picture of boats through our network, right? And we'll get out a predicted label, right? And either that predicted label will say boats, in which case the error, we're happy, our network did a good job, right? We shouldn't change our weights. Or it's going to say, well, that's a picture of cats, which is wrong, in which case there's an error now, and we should use gradient descent, take a gradient step to move from saying it's a cat to saying it's a boat, right? Hopefully that makes sense to everybody. Clear? Hopefully clear. So now let's just talk about this choice of architecture, right? Which is totally an art, right? There's a whole menagerie of deep networks. I mentioned convnets. Turns out people don't use convnets as much anymore because they use these things called resnets, right? And they use these things called dense nets. What are these networks? Well, these are networks where you have this same exact structure we just talked about, but you have additional connections that just jump around or short circuit a layer. So in a resnet, the output of this red resnet layer, this red layer, is going to be not only the output of that layer, but you're also going to just add X, right? And then the output of this blue layer will not only be the output going through that blue layer, but also you add in the input, right, to that layer, which turns out to also have X in it again, right? And so it's basically short circuiting. The reason people use resnets is we can state it, very, very clearly. It turns out that there's really no reason, like if all you care about is approximation power, there's no reason to differentiate between or prefer dense nets over resnets over convnets. Why? Because all of these networks have universal approximation capability. What do I mean by that? Is if you have enough breadth, meaning enough units in every layer, and if you have enough depth, lots of layers, then you can approximate anything. Okay? And so any of these networks can approximate anything. So that's not why you would choose resnets or dense nets over convnets. But it turns out they're not the same when you try to actually do gradient descent learning. Okay, they're not the same at all. It turns out that resnets are like way better for optimization than convnets. Learning converges faster and much, much more stably. Okay, and so this has been just a big open question. Because if we can understand this, then we can actually hopefully have a way of saying, well, this new Nathan net is even better than all those because it has this property. So let's look at one way that we can think about this. Up until now, this has only been studied. It has only been studied empirically. And here's the kind of plots that have been generated. This is from Tom Goldstein's group at University of Maryland, his beautiful paper, where they basically looked at low dimensional projections of the loss surface. What do I mean by that? So we're trying to use gradient descent to fit a deep net in a certain approximation problem. Let's say that we're using the two norm, the mean square loss, or the squared loss between the true output that we want to see and then our inferred output, right? Y and Y hat. Okay, well, because the network is no longer, because the network's nonlinear, right? You're not going to, even though the output, the squared loss is a convex loss function, right? In terms of the parameters, is highly non-convex, right? And so, and it's also, if you have a zillion parameters, the parameter space is a zillion dimensional. So how can you even understand what goes on? Well, what Tom and Goldstein did is they looked at low dimensional projections of the loss surface, And this is what they saw, right? And this is fantastic, great empirical evidence of why a ResNet is nicer to optimize than a ConvNet, because a ConvNet has a jillion local minima, right? That you're going to get stuck in, right? Whereas a ResNet is just nice and smooth, and you could just totally imagine, with some any kind of reasonable scheme, being able to find the bottom, right? The local minimum over this particular region. Okay, but everything to date has been empirical, but it turns out that we can apply everything we just talked about to prove theorems about this, right? And the spoiler alert is that we're going to prove theorems saying ResNets are better than ConvNets. Okay, so let's start by defining a spectrum, kind of a pun. You'll see spectrum of deep nets. What is the spectrum of deep nets? Well, if you look at just this term here, this is the deep net that we've looked at up to now. If W is a convolution matrix, then this is a ConvNet. And how do you get a ResNet? You basically add, remember, you add the input, right, to that particular layer. And so what we're going to do is we're going to add on rho times the input, so we can have a spectrum of deep nets where if rho is 0, you get a convolutional neural net. If rho is 1, you get a ResNet. Okay, hopefully that makes sense to everybody. And we're going to study the optimization landscape as a function of this rho. Okay, and we're going to, turns out we can do more, but we're just going to focus for right now on regression problems, function fitting, or operator fitting, and we're going to focus on mean square error loss. Okay, but this is still lots of big time applications are to solve regression problems with mean square loss. Okay, so let's start to pull out some of the results that some of the things that we can say. Well, the first thing we can say is, remember, with these deep networks, they are a continuous piecewise affine approximation to a function. Well, it turns out if you just look at them from a different angle, an angle not in terms of the input, but in terms of the parameters, well, it's easy to show that all of these deep nets we've been talking about have a loss function that is continuous, piecewise quadratic in the parameters, right? In the entries of the W matrix and the B vector. Okay, here's a picture on the right of a piecewise quadratic function, right? And of course, what a deep net optimization is trying to do is find the bottom, right? Find the bottom of this piecewise quadratic loss function. Okay, so this is nice because we can study, if we can study this piecewise quadratic locally on each piece, right? Maybe, and do things like find bounds, maybe, on certain properties or certain quantities, then we can say something about this entire surface, right? And so if you think about the local geometry of this piecewise quadratic, tile by tile, then it's piecewise quadratic, so that's the singular values of some matrix, right? The Hessian matrix is what's going to determine the local how this piecewise bowl looks like. And it's a matrix that I'm not going to write down here, but this matrix depends on the weights, the biases, this rho parameter, the training data, and the particular region that you're in. Okay, and so we're going to study the singular values of this. Think of it like a Hessian matrix. Okay, and why do we want to study these singular values? Because the singular values tell you about whether locally this piecewise quadratic loss function is really nice and has kind of spherical kind of structure, or if it has really elongated eccentric structure, right? Just from the theory of optimizing quadratic loss functions, not piecewise quadratic, but quadratic loss functions, you know that the more elongated the loss, the isocontours of the loss function become, the harder it is to optimize. In particular, because the gradient doesn't point to the bottom anymore; it points like just off It just doesn't point to the bottom. And so this eccentricity, again, if you remember back to just simple L2 squared loss optimization, the eccentricity is controlled by the condition number of the matrix, of the Hessian. Okay, and remember the condition number is the ratio of the largest to smallest singular values. Okay, so what we're going to do is we're going to look at the singular values of this Hessian-like matrix on each one of these pieces of this piecewise quadratic loss function. And that's going to allow us to tell a difference between different deep net architectures. Okay, so we can prove the following theorems, right? For rho equals 0, okay, that corresponds to the convnet case. Okay, well, it turns out that things are bad, right? The condition number of the local loss function is not bounded. Okay, so that's not good, right? That means locally this piecewise quadratic loss function can have really bad geometry, right, for optimization. On the other hand, if rho is just epsilon bigger than 0, right, you don't have to go all the way to 1. Just as soon as a little bit of the input is allowed to leak around the layer, you can bound for each region, partition region, you can bound you get nice bounds on the local loss function. And you can even find a uniform bound over all partition regions, right? And we have a formula for this. Okay, so why is this useful? Well, what this tells the practitioner, right, is that provably, we see proof in picture in the right here, but provably, right, for all resnets and all convnets, the loss function of a resnet is better conditioned than a convnet, right? It's nicer, right? It's less erratic. It's less eccentric, right? It means that if the local minima are more easily found using gradient-based optimization, right? And so we're really quite excited about this because it's the first actual analytical proof that resnets are better than convnets. And the great thing is that this could be not only applied to other networks, but it's going to inspire people to come up with new architectures that, using tools like this, are even easier, for example, to optimize, because optimization is incredibly expensive, right, for deep nets. Okay, so let me just, is it okay if I go 5 more minutes? I don't want to overstay my welcome.
Yeah, sure, go ahead.
Okay, so let's just do 2 last applications, and this now has to do with generative networks. What are generative networks? These are the kind of networks you hear about, synthesizing pictures of people, for example, right, or scenes. And what a generative network, it kind of runs backwards from a classification network. You start with a low-dimensional input, right here. It's usually called Z. And then you go through a generative network that increases dimensionality as you go through the network, and then it outputs a picture. And this is an actual synthesized bedroom image. It's just insane, right, how well this works. So just for every different entry of Z in this low dimension, maybe 100 or 1,000 dimensional input space, you get a different bedroom picture, right? And then how do you learn these parameters theta? Well, there's a whole host of different methods that you can use to learn these values theta. Okay, so these are generative networks. So what I want to just talk about just briefly is this learning process. And there are 2 kinds of, really 2 families of deep generative networks, DGNs. One are deterministic methods. These are often trained using this voodoo idea of game theory, and they're called GANs. I'm going to talk about the other approach with probabilistic deep generative networks. And here we're basically trying to do probabilistic fitting. Okay, and so here's the basic idea, right? If from a probability standpoint, we have an input that's a unit Gaussian, let's say, or uniform distribution. We have data, right? These data points, the black dots here, they're samples from a true data probability distribution, this blue distribution in some high dimensional space. And what we want to do is we want to learn the parameters of this theta learn the parameters theta of this generative network. So we can take this isotropic unit Gaussian, spherical symmetry Gaussian distribution in low D and map it up into high D so that warp it so that its warped version, this green distribution, is close to this blue distribution, right? Let's say in terms of some probabilistic loss function like some kind of entropy or Kullback distance. Okay, hopefully that makes sense. So how is this done in practice? Well, it turns out in practice, this is done using extraordinarily crude approximations, like assuming, because it's very hard. It has been very hard to like compute any of these properties, compute the likelihood, compute the posterior of this green distribution, and so people resort to really crude independence assumptions, and these fall under this idea of variational VAE or variational autoencoders. And what I want to just tell you about today is that it turns out, because we know so much about the spline properties of deep nets, we can just do a lot better. Okay, and here's how we can do better. Well, the first thing that we realize is that a deep generative network is again just a CPA spline, but now it's going not from high D to low D, it's going from low D to high D. And so basically it's a manifold mapping. Okay, so you can think of the input space of your deep generative network. Okay, the input space is, let's say, two-dimensional in this case. As we go through the network, we're going to be throwing down hyperplanes, right? Just like we talked about, they're going to be folding. So we're going to be partitioning this two-dimensional input space. Here's an example of that. But then what is the network doing? In this case, it's going from 2D to 3D. What the network is doing is it's first partitioning this input space like a piece of paper, but then it's taking this piece of paper, it's actually a rubber sheet, and then it's actually taking and it's embedding it in 3D as a two-dimensional manifold. Okay, so it's creating a two-dimensional continuous piecewise affine manifold in 3D. Okay, and where each of these tiles, this purple tile here, for example, is stretched right in two directions, and then laid into this manifold so that the resulting manifold is continuous. Okay, and so it's basically just a manifold mapping. Okay, why is this interesting? Well, this is interesting because we can compute all kinds of stuff. Okay, in particular, if we think of putting down a probability distribution on this input space, let's say it's a uniform probability distribution, okay, over this 2D plane. Well, it turns out that we can actually compute, right, because we know the area of this originating tile, and we know the area on the manifold after it's warped. We can actually compute the probability that a point from the probability of this particular piece of the manifold. Hopefully this makes sense, right? It has to do with the area of the original tile, and then the amount is warped, right, by this mapping that takes you up into 3D. Turns out that allows you to get analytic formulas for everything that goes on up here in the high D space. And you're able to compute, for example, the likelihoods that you need. And that means you can resort to classical, instead of like really bad approximations, you can bring in the classical methods that we know work really great for learning probability models. Things like the EM algorithm, expectation maximization algorithm. Why is that cool? It's because we know that this performs really well in practice, and you have guaranteed convergence, right, to a local minimum of the distribution. Okay, and so it turns out this works really well. Here's just an example. Let's just look at this one example. Here's some data points that lie in 2D along these points. Here's learned using this analytical EM algorithm that we have, that, by the way, is gradient free. You don't have to do gradient descent or anything like that. It's just E steps and M steps. And here's the comparison learned using, again, this variational autoencoder approach, right? So just much better performance, guaranteed convergence, gradient free. There's just a lot of great things about this. I think I probably need to stop. Is that correct?
We still have a couple minutes if you want to conclude.
Okay, yeah, let's conclude. Let me just say that the same idea can be used to, this idea of warping the probabilities as you go from low D to high D can actually be used to understand why why deep generative networks produce biased imagery. Okay, which is very, very important. Just think of the problem of wanting to create a generative network that generates pictures from different genders, for example, with an equal likelihood. Okay, well, it turns out that using this idea of the space warping, mapping from the low D space onto the manifold, you can actually take any learned deep generative model and actually account for this warping so that you can actually make the images that are output less biased and more fair. Okay, so there's all kinds of interesting practical applications of this. So let me just end, right? What did we talk about today? That all of this was possible because we recognized this spline aspect, right? There's lots of things we talked about, but the bottom line is this two-part yin-yang aspect of CPA spline approximation, namely fitting the partition and then fitting the approximation on top of the partition, that by understanding both of these processes, we can really understand a lot about what's going on globally, right, within a deep network. So I'll end there and just happy to answer any questions in the time remaining. Thanks so much again for the invite.
Thank you for this amazing talk. Very, very informative and amazing.
Thank you. Hope it was clear enough.
We're definitely going to be using. So let's see if anyone has any questions. Maybe I'll start. So when you're making the analogy with or not the analogy, but using spline ideas to prove things about neural networks, is it agnostic to activation functions, or does it have to be ReLU?
Wow, great question. So it is, yeah. So there's two kinds of two kinds of results. The first is if the activation functions are piecewise linear, so ReLU, leaky ReLU, absolute value, these are all used. Yeah. Then everything is everything's identical, right? Nothing changes whatsoever. If you come up with some crazy new piecewise linear with like 3 regions that has 3 pieces, same thing would, if you just have 2 hyperplanes, right? Instead of 1. So everything works out the same. If there's 2 things you can do though, but then you say, well, what about sigmoid, right? Come on, right? So there's 2 ways to handle things like sigmoid. One is by approximating it using piecewise linear approximation, and then everything would work, but that's not pretty, right? That's kind of ugly. But there's a way more elegant thing. Okay, and basically here's what in a nutshell, here's what it is. So let's just go back to this hyperplane idea. Well, no, just this hyperplane arrangement, all these tiles, right? So what we said is that an input falls into a tile, and it's in a tile or it isn't in a tile, right?
Yep.
Okay. So this is what's called vector quantization, and this is what's called hard vector quantization. It's sort of classic, approach. Okay, but there's another thing you can do. You can take a probabilistic argument, and you can do what's called soft VQ, and then it's a little bit like a mixture model. That basically it says if you have an X that's in a tile, well, you just know that it's in that tile with high probability. It could actually be from a neighboring tile.
Yeah.
Right? Makes sense? Well, It turns out if you do like a Gaussian mixture model like approach, or just soft VQ,
Yeah.
Well, and if you just push the math through, you get a spectrum of activation functions. At one end is ReLU, okay? But at the other end, when you go fully probabilistic, you actually get linear gated sigmoid.
Oh, interesting.
Beautiful, right?
Yeah.
It's just, and it's like, it is literally like what you would use in a network. And so yeah, and so now this gives you a whole spectrum of activation functions to explore.
That's interesting. And then your
yeah,
bounds still apply in those cases?
yeah, they would apply. You would just now have kind of some probabilities hanging around, right? So you do things like in expectation and stuff like that. Yeah, great question.
Nice. That's nice. Great. So Zach has a question.
Yeah, thanks, Joe, and thanks for the great talk, Richard. I was curious about you had the condition numbers in the piecewise quadratic ResNet. So for optimizing that sort of thing, I imagine it's like a constrained optimization problem, and a lot of the optima might lie on the hyperplanes. So I was curious, in your results, do you look at the boundaries of those Voronoi cells and have a corresponding quadratic form Hessian matrix on those, or is it just in the interior of the Voronoi cells?
Yeah, that's well. I'll just have not, but that's very interesting. Yeah, have not, and that's definitely something that could be neat to look at. Yeah, that's a great question.
I'd be curious about empirically, how often is the minimum that you find actually on the boundary of those cells? And
one would presume high probability, right?
Awesome, thanks.
Yeah, very interesting. Yeah, that's cool. Hadn't thought of that. Yeah, neat.
A couple questions from the chat. Alexander asks, is it possible to optimize deep net structure by step-by-step simplification of the loss function layout?
Ooh, interesting. It's a chat question, so maybe hard, but could they elaborate a little?
Alexander, maybe you can mute yourself.
Maybe he can just jump on microphone.
I just unmuted if you want to ask or not. Okay, so
let me think about it. Why don't you send me an email and we can talk about it?
Okay. Maybe you can go to the next question. Any thoughts about temporal dynamics or recurrence? They're like the other side of the coin to the ResNet peek ahead.
Ooh, so does that, by that meaning does that meaning like recurrent neural networks?
Yeah, actually, I'll unmute Eric. Eric, if you want to ask.
Hello, Eric, my friend.
Hello, Rich. Cool talk.
Eric and I go way back, everybody.
Yeah. So Rich changed the course of my life in the late 90s. Introduction to EE class, he's the best. But today, I wanted to ask you, so I love peeking ahead with a ResNet, but
sure.
I want to peek back so that I can do recurrent connections, and I experience much more smooth empirical training, just the black art when we use recurrence. But I'm curious if you have any idea of where to bite, where to sink your teeth into doing an equivalent kind of analytical.
Oh, interesting. Yeah. So are you talking about building a ResNet like RNN, or just using some kind of recurrence when you're learning a feed-forward net?
Well, I was thinking the former. If you think of a ResNet as just teleporting inputs forward, and then a recurrence is just teleporting inputs backward.
Right.
I would expect there to be some sort of symmetry of maybe.
Yeah. So this. Yeah. So we. Yeah. Let me think carefully here. We should be able to analyze that, and well, we can analyze it. Just the question is how hard it is, because we have everything we need. So, because I talked today about the idea of skip connections and ResNets and these singular values, but in another line of work we have looked at the spline approximation of like RNNs, right? So like going back, like you were saying, like back in time and not just forward in time. And so I would expect that by combining those two lines of work, we should be able to do what you were, I don't know the answer, but we should be able to do what you were, hoping. So yeah, that's a really interesting idea. You must have had great training. How did you have such a great idea? No, that's neat. Let me think about that. Yeah, that's really neat.
Okay, well, figure it out and then I'll read it.
Okay, yeah, great question. Great question.
Eric, you should have said, figure it out, make a little Python package for me, and then I'll use
yeah.
it.
I'll read the comments. That's funny.
So just one last question before.
Sure.
So can you use these? You sort of showed us geometrically how the analogy or the use of splines in deep network. Can you use that to interpret what the deep network is actually doing while training, like visualizing what the layers are doing and why they're failing, or what regions they're doing, things like that?
Great question. That's a great question. I would say one would expect so, right? We have not really looked at that, right? But but that's a great question. One would think that you could. I think the tough part is that there's a lot of regions, right? That's like this didn't affect us when we talked about like the singular values, because it's in, it doesn't matter how many regions there are. We can have a bound for ResNets at every single one, right? The condition number is bounded, so we're okay. But there are like a gajillion regions, because like they're, just think about one layer, right? You have a 10,000 outputs, you have 10,000 hyperplanes. Now think how many regions are formed. It's like it's like quadratic. It's like you get an exponential explosion, right? And so there really are a huge number. And so I think the key thing is somehow to figure out what is the right visualization or dimensionality reduction that would be useful. Yeah. And the other thing that's just fascinating is, of course, nearly all these regions are empty.
Right.
There's no data point in them, right? So, but they're a byproduct of this subdivision process, right?
Right.
So, yeah, just the whole idea of visualizing in some way is, I think, really interesting. It's a great question.
All right. Thank you very much for this great talk. Hopefully next time we see you in person. And
I appreciate the invite.
Great to see you, Rich. Thanks for being here.
Oh,
awesome.
It was fun. Thanks for the question, and thanks for setting things back on track, because I was a bit unclear. So that was a great question.
That was great. Thank you so much.
Okay, see you, everybody.
Thank you all.
Have a great rest of your spring.
Yeah, that's right.
Thank you. You too.
Okay, ciao.
All right.